Now. So yeah, let me briefly introduce our next speakers for the hands-on sessions. So they will be the speakers for the two hands-on sessions today and tomorrow. They are from the Cavity Quantum Electrodynamics group led by Professor Helmut Rich in Innsbruck. It's a theoretical group, and the tutorials will be about a library or a package that they wrote for Julia or in Julia for simulating quantum systems. The main creators are Sebastian Kramer, and the maintainer, or the main maintainer for a while, was David Blankenstein. And right now we have the pleasure to have Laurin Ostermann and Cristoph Otta. Cristoph is a third-year PhD student in the group. He's working on super-radiant effects of dipole interacting clocks, atoms or something like that, yeah? Good. And Laurin Ostermann, he's a senior scientist in the group, if I'm not wrong, right? Perfect. And he is also working on super-radiant radiance in optical fibers and waveguides. So yeah, I let you the floor, and yeah, you can start the presentation. Thank you.
Welcome, everybody. Can you hear me? Is that fine? Or should I maybe move it up a bit? Like this. Okay. All right. So thank you very, very much for this introduction. And first of all, also thank you very, very much for inviting us here. I know how much work it is to put such an event together, and it's really amazing how this turned out. And I'm really happy to be here in Lausanne. Yeah, as Ivan said, it's me today. I'm Laurin Ostermann, and it's Cristoph Otta. We're going to do the tutorial hands-on session on QuantumOptics.jl, introduce Julia a bit, especially what we do with the Julia language. We had this very nice overview and introductory presentation yesterday by Filippo, which I really appreciated. So we all should know a bit what Julia is now, so that we can use it. And apparently you guys, I was watching yesterday from behind, you all seem to have installed it somehow and more or less have it working. But before we get started, I'll give a brief introduction. And while you can listen to me, or maybe also not listen to me, and make sure that your system works, please add, if you have not done so, these two packages. So please go into the package manager, which you can call by pressing the closing square bracket, and then make sure you execute add quantum optics, and once this is done, make sure you execute add pyplot, so that we have those two packages. And sorry? No, okay. And then maybe also in a notebook environment, or also in the REPL environment, make sure that if you type using quantum optics and using pyplot, that this actually works, because when you call it for the first time, it will attempt to compile the package and bind everything together. And if there are some errors there, we had something apparently on Arch Linux, there are some issues. So please make sure you do this while I give a short, like 15 minutes or so, introduction about the package and the history of the package. All right. So, here we go. So this is what we have in mind for the two sessions. So we have 2 hours roughly today, and we have another 2 hours tomorrow. The session is called Hands-On with QuantumOptics.jl. So we're really happy that you all brought your laptop books, and we're going to be using these quite a bit. We have some examples where you can follow along, and then we'll have some tasks for you which you can execute individually or maybe in groups. So I would also ask the more advanced Julia and QuantumOptics.jl users, so if you already know about this, maybe look around a bit and help your peers out if they're a bit less experienced with the package, so that everybody can leave today, and especially tomorrow, with some nice learnings about the package, and especially about how to use the Julia package. Okay, so the outline is I'll give a brief introduction and a little history, tell a bit about how the package was conceived and how it was developed. And then we're going to already step into the code, and all the coding will be done by Cristoph and Raphael, who is also here from our group, and I will be walking around and helping you if you need anything, so just call us. All right, the first guided example will be a single qubit where we introduce sort of the language of, that we use in QuantumOptics.jl and show you how all this is done. Then we're going to have an exercise for you, a really hands-on task where you can program something that actually pertains to quantum computing. So as Ivan said, we're quantum opticians. We're not in quantum computing, but any quantum computing platform will at some point need some realization. And this is done in various ways. And today we're going to have you program ion chain readout procedure. And tomorrow, that's the stuff that we have here in italic. There's going to be another guided example about a dispersive readout procedure, semiconductor qubit setup. And then we'll have you, this is basically the exercise, the sort of takeaway workbook that you will go home with. Either program the Möllmer-Sørensen gate or the cross-resonance gate. So again, one's for the ion platform, and the other one is for the superconducting qubit platform. Okay, jumping into the history. So we've heard some names for her by Ivan, and I will just flash some pictures here. So the package was conceived in principle by Sebastian Kremer in 2015, 2016. He was really eager to program something that takes a lot of the day-to-day work, repetitive work out of our programming tasks, and I will come to this. And it's actually his second attempt. He was already doing something in Python before, but then Qtip came along, and basically they had much more manpower, and so it didn't really make sense for him. At least that's how he claims, to continue his work in Python. That was in 2010 or so. And when Julia came out of MIT, he was really excited, telling everybody about this. Then basically just writing this entire quantum optics framework in Julia again. And in the beginning, he even wrote own, because differential equations.jl didn't exist back then. He wrote his own dormant Prince differential equation solved, so that really everything could be done in Julia. So Sebastian defended his PhD in 2016 or 17, I don't remember, and then decided to go to industry. And David basically took over the main task of developing further, and also doing a lot of the maintaining work, and looking at the GitHub issues and answers. And David is also a guy now since 2 years. He also decided to go into industry. And now Cristoph is, besides his research, basically doing these tasks of helping people and addressing the GitHub issues and also the Slack channels. And I'm also trying to help a bit, although I have to admit that my time in this is a bit too limited, to be quite honest. And of course, there's Helmut, Professor, our group leader, who's had experience in numerical dealings with quantum optics since the early 90s. So he's actually one of the people who invented the Monte Carlo wave function solving idea. I'm sure you've all heard about this at some point. Okay, so this is the team, and let me move further. If my click clicks, no, it doesn't. Now it does. So how did this come about? In principle, in the beginning, in Helmut's group, so Helmut is really the seed of this, amongst other sort of long-standing researchers, distinguished scientists in the field of quantum physics and numerical simulations. But in the beginning, sort of every PhD student, every master student who joined the group did their own numerical framework, in a sense. So remember, one very important aspect that I should mention here is all these packages do is matrix multiplication, in principle. If you break it down, it's matrix multiplication. But it's matrix multiplication of, first of all, huge matrices, and secondly, a lot of the same stuff happens over and over again, and you can confuse yourself infinitely many times, in principle. But in the beginning, there was just this self-made thing. Then, I think in the mid-90s or end of the 90s or so, the quantum optics toolbox in MATLAB was developed somewhere in the University of Auckland. And this was used quite a lot, but again, there were some convenience methods. In principle, they could let you build operators easily, but it was still sort of just, well, shortcuts for writing down matrices. Then, in Helmut's group, C++ QED was developed by Andras Vukic, a very talented programmer, and yeah, physicist also, of course, a very talented physicist from Hungary. He's now a senior scientist at the Wigner Institute, Wigner Research Center in Budapest, and he developed these simulations in C++, and that's why the package is called C++ QED. He's a brilliant programmer, a brilliant physicist, so brilliant that almost nobody else was able to use the package, unfortunately, because, little anecdote, he believes that his code is self-explanatory, doesn't comment the code. And now, I mean, if you go look now, I don't want to do injustice to him, so he's really a nice and brilliant guy. Now, if you look, there are some documentations and lots of tutorials, but back in the time when this was conceived and relevant, it was absolutely impossible for almost anyone else besides him or with his help to actually use the package. But it's extremely efficient. Of course, it uses the bare metal C++. And sometimes we say QuantumOptics.jl is like a Mercedes. It's nice and it's fast, and C++ QED is like a Ferrari. It's even nicer and even faster, but you really have to know how to drive the Ferrari, and the Mercedes just takes care of you. Okay, so I mentioned Sebastian did this PyQ or whatever package in Python, but this was completely beaten by the fact that then QTIP came, and I'm sure you've all, I mean, anybody who's doing quantum physics and has ever done any simulations, I guess, has not managed to not use QTIP, and we really like this package, and we also used it quite a lot. But then, as I said, Sebastian came with this idea and was extremely excited about Julia, and this is how, well, over the years from 2016, intense years, until 2018, and then in 2021, last June, we took it actually to version 1.0. This is how QuantumOptics.jl came about. And last introductory slide, and then we'll really get to the programming. I'll tell you three main sort of aspects about why we think that QuantumOptics.jl is such a nice package and why we love presenting it here and try to teach it and try to provide tutorial resources for it and all those kinds of things. So first of all, we really like the performance. We've seen yesterday in Filippo's introduction that all the packages that sort of are intertwined, that gear into each other, sort of are all written in Julia, and this gives you a nice advantage in terms of performance and also in terms of maintainability. And as I mentioned before, Sebastian, in the beginning, when differential equations.jl didn't exist yet, he wrote his own solver. At some point, Chris Rakaukas from MIT approached us, so we approached him somehow. He was using some stuff for his bio simulations, and we were looking for differential equation solver, and we got talking. And it was reasonably easy. I mean, this differential equations.jl does have some nitty-gritty parts, but it was reasonably easy to just swap out the differential equation solver, that is basically the heart of all the time evolution and all the dynamics that we do in the simulations, swap that out by differential equations.jl, and this also gave us a nice speed improvement. So already this sort of, gearing into each other, these different packages is demonstrated by this, and it gave us a nice performance. Secondly, we wanted to have it really usable. So a lot of effort in this package has gone into tutorials, into tutorial notebooks, into documentation, into also. So we really make sure that everything we use is robust, and any time we do a test, we usually test it against physics. So that's the big advantage that we have in physics. If we want to test a routine or basically a calculation that we perform numerically, usually or hopefully there is either a measured result or an analytical result which you can take to compare it against. And we do this here for basically all our methods and really make sure that it's documented and it's also robust. And this also brings me to the last thing. We really want to make sure that it's reliable. We try to embrace the open source idea and really try to bring an international community together. And I mean, this summer school here and the fact that we can teach it here is some proof of this, but also there are many people who follow us on GitHub and many people who contact us use it in their research. And in user-friendly and a reliable framework. And I think we're at a point where the framework has grown sufficiently much that we've sort of achieved this goal. And of course, we all hope that you guys, to some extent or another, will contribute also to the future well-being and to flourishing of this framework, as I said. Okay. Please remember this URL, and if you haven't done so already, please open your browser and go to this URL, qojulia.org. This is the homepage of the package, and this is basically where you can find all the resources. And there is one extremely important resource which you will use a lot if you're dealing with this package, and that's the documentation, which you find up here in the top right corner. And if you click on this, you will go to the documentation page, and there's a nice field on the upper left-hand side, and basically everything, also in terms of the underlying physics and the underlying thought processes, if you think about master equation solvers, stochastic solvers, homodyne measurements, Monte Carlo wave function simulations, also the ideas that lie behind the framework are all explained here. So if you have some time, the documentation is really rich. And if you find some typos, please pull request, that would also be nice. But everything basically is written up here, and you can use this as a resource. And the second URL that I would like you to open now is a little page that we made for the notebooks, for the Jupyter notebooks that we're going to be using here. So if you go to qojulia.org/QCHS, you will find a nice little web page, and the right-hand side is not filled yet because the right-hand side is for the notebooks that we're going to use tomorrow. But on the left-hand side, there are two packages or two downloads, and we're going to start with the first one, where we're going to now have Cristoph show us in a guided demonstration how we can implement a single qubit, and then we're going to switch over to the hands-on exercise where you can implement an ion chain readout. And with this, I'm going to switch over to Cristoph. All right.
So the first example, as Laurin already mentioned, is a single qubit. And this basically should just show you that there are different ways to implement a single qubit, and that there are different methods to solve the dynamics of this single qubit system, or in general for every other system. So this applies for all different systems you want to implement. So today we just have this single qubit, which is just one system, and it's not a composite system. Tomorrow we will deal then with composite systems, and yeah, just to mention this at the beginning. Yeah, good. Okay, then just start. Just start by using the quantum optics package and by also using biplot. So biplot is just needed to plot all the results we will have. And this might take a few seconds in your case, but I pre-compiled it before, so in my case it was a little bit faster. Which describes a two-level system, basically. And these things are implemented in quantum optics, and to find the spin 1/2 basis, we just type spin basis, I guess, right? And I'm just typing it that I'm slow enough that you can follow everything. If I'm too slow, then please just tell me, then I copy-paste it in and explain it. But I think to get all of you which are not familiar with Julia, now it might be better that I just type it and explain it in the meantime. Okay, so this is how we implement the basis. On this basis, we define the operators, which is, for example, the sigma m operators. And this sigma n operator is defined on the basis of the spin 1/2 particle. And this is one crucial difference to biplot. In biplot, you don't have these things like bases, or maybe you have, but in Julia, so in quantum optics, we really look for the right basis if you multiply two operators. If it's not the right basis, you will get an error that this is not possible to multiply. So multiply two operators, they always need to be defined on the same basis, which yeah, is really nice to get the right physics and you don't fool yourself, basically. Good. Okay, then I need to define the sigma minus, a sigma plus operator, which is just the dagger of the sigma minus. And then I also define the sigma x operator. Which is just sigma x of B spin. And I also define here the 1 operator, which is just the 1 of B spin. Okay, and then I hope it's working. Good. So here you see that the output is always the last line in the box, and what you see here is just a 1 operator on the spin basis, which is just a diagonal matrix. Good. So you know how to execute the boxes, right? Just with Shift Enter and what else? Yeah, nothing else. Okay. Then already your first task, which should be quite easy, verify these 3 relations, what you see here numerically. Just implement a comparison between them. I think like in 2 or 3 minutes you might have it. If you have problems, then just tell us. So I will not this. Okay, I defined the initial state, which is just an n-level state, which is living on these on these bases here, on these 2-level bases. And a lot of you made this mistake that they either use the psi from before, which is still defined on the spin 1/2 basis, and this is not working because then the matrix for the 2-level basis is not compatible with the spin state. They have the same dimension. They basically are the same for these 2 cases, but actually the package is built up on this, that you are not allowed to multiply different objects with different bases. So that's basically the point of this. How I did it here is just defining the Hamiltonian as a function of delta, and I just solved the Schrödinger equation once for 0 detuning and calculate the expectation value, and then for omega over 2 detuning. What also a few people made wrong is that they also used the sigma operator for the expectation value here. So they used sigma plus times sigma minus, which is in principle right, but you can't use it because the other one is again implemented on the spin 1/2 particle, and this one is on the n-level basis. So is this so far so clear, or good? Yeah? Yes? Yeah, but I already captured the excited state population here. Yeah. But it's true. Yeah. Okay. Good. And then I plot the result, and it should look like this. If you have a detuning, you don't have full Rabi cycles. You don't go up. The Rabi frequency is also then a little bit different because it's given by something over detuning squared or so. Yeah. Anyway. Good. Do you still want a solution that everything has it right, or because maybe just define the Hamiltonian with this function here, because I use it in this way in the next steps. So I give you just 1 or 2 more minutes. We just have looked at a closed system, which is described by the Schrödinger equation. And now we want to use the master equations because we want to do one, for example, with decay of the atom. And I put in a link here with a description of how the master equation is implemented. You can have a look at this if you want. But what we basically just need to do this is, okay, I just define my Hamiltonian as with the function from before. However you did it, just use this one with the detuning when it's 0. Then I just need to define my rate and my jump operators for the jump operators for the atom, and if you want the atom to decay from the excited state to the ground state, it is just a sigma 1 2 operator. And yeah, the thing we also need is just the rate, and this is basically the decay rate of, it's just the decay rate of the atom, what we defined before. And if we want to solve this now, we can basically copy-paste this thing here, because it's nothing else as replacing Schrödinger by master, and we also have, okay, I cannot copy-paste it. And we have some additional information or some additional inputs, which are the jumps of the system, so the decay process in our case, and the rates of the system are brought to the function with this keyword argument. So if this keyword, so these are called keyword arguments, if you don't put anything there, it just assumes that the rates are 1. So you also could just make an operator which includes the rates with a square root, and it would also be fine. So that's basically the same. Good. Yeah, and then we just calculate this, and we get the following. Okay, so this takes a while again, because it's the first time it's executing the master equation, and also the master equation has a dimension of 2 times 2, which is 2 more equations. But yeah, anyway, in this case. What you see is that you get damped Rabi oscillation, as you would expect. So that's basically how you implement the master equation. And the point what I want to show with this is, if you have a Hamiltonian, which is or if you already implemented the Hamiltonian and you just want to describe also the interaction with the environment, and you know how it is described with the jump operators, it's super easy. You just need to change Schrödinger to master, implement the jumps and the rates, and then you're already done. So then you're already finished. Good. Then the next task, quite easy task, replace master by Monte Carlo wave function and look what's happening. Replacing really master by Monte Carlo wave function, and what you get is just a single trajectory of your time evolution, if it's working. Okay, in this trajectory we don't see a jump. What you can actually do is that you obtain always the same trajectory. You can set a seed, and if you want to change different trajectories, then you just make an iteration of this seed, which is useful if you want to reproduce results. You usually use a seed that someone else somewhere with his own computer can produce the same results. Yeah, and if I do this with seed 1, I have like 4 quantum jumps, and yeah, anyway, if I have seed 3, then I don't have a quantum jump. Okay, so far so good.
We've been asking you to average over lots of trajectories, and of course all of you figured out that this will imply a for loop of some sort or so. Then if you try to look at the syntax or try to find out how you can put that into suitable variables in order to do the averaging afterwards, there is also, of course, besides the QuantumOptics.jl documentation, which is specific about the package, of course, there's tons of documentation about Julia itself, where the syntax of the language is explained. And as all of us do probably every day, if you Google it and if you put Stack Overflow or Stack Exchange behind it, you will certainly find someone who has done such a code snippet, and there is lots of resources for Julia as well. So maybe that's also a nice hint or so if you haven't thought about that yourself, to maybe just check those resources as well.
Basically what I did is just defining an empty list with all zeros. I did it here for 500 trajectories, and what I do, I just calculate the time evolution for different seeds to more or less make it reproducible, then calculate the expectation value of this as we did before, and then I just added to this list of 0, I just added the calculated value. Do you have a question? Or no? You were just like, okay.
Why is there a dot in front of the?
Because if you don't put the dot, it tries to add a vector to a vector, which is fine. I could be. Let's see. Try it. Yeah, that might be fine. Yeah, but I thought I just need to add element-wise. But I think, yeah, it's the same. Right. Okay. Yeah. And what you see from the physics perspective is if you have enough Monte Carlo trajectories, it's approaching the master equation on average. And this doesn't really make sense in our example with a two-level atom, because if you do the master equations, it's basically just four values you need to calculate, and with the two-level atom in the Schrödinger equation, or with the Monte Carlo, it's basically just two values which are stochastically, basically with jumps, and you need to add up a lot of equations, in my case here 500, to get an approximate solution. But if you imagine that you have a state which has several thousand or maybe even 100,000 state, let's call it, how to call the Einheiten, also the, huh? What? Entry, okay. Which has like 100 or 1,000 values or something like this in the vector, then it can be beneficial to just average over it, because the density matrix always scales with the square of the size of the cat. Yeah. With the state vector, exactly. But I think you already know about this. Good, so that's basically this example. We have 15 minutes left for the more involved example. So if someone still wants to do this, you can also just finish this. It doesn't matter if you not finish anything, so just do whatever you want. I just go to the next example, which is the ion chain readout. I guess most of you know what the system is describing, but maybe I just explain it in a second. So level 1 and level 2 is building your qubit. So level 2 should be a state which does not decay at all or has a really long lifetime. And the level 3 has a really fast decay rate into level 1. And how you read out the ions in the ion chain is just driving the transition from 1 to 3 and detecting the photons which are scattered from this transition into all directions. And this means this excited state 3 needs to have a really huge decay rate that you can collect a lot of photons. And what this basically, so how you describe this basically is just with a Monte Carlo wave function, because every jump, as we heard yesterday, every jump is just like emitting one photon, and this is basically then the maximum what you could get in this detection scheme of if it's in the excited or in the ground state. Yeah, maybe I should also mention this. The point why you could detect if it's in the excited or ground state is if it's in the excited state, the state does not couple to state 3, so nothing will happen. You don't detect any photons. If it's in the ground state, it couples to the state 3, and then you get all these photons from the decay of the excited state. Okay. We should finish actually, because it's late. Okay, I basically just show you how I did it. Of course, we need to load first quantum optics pipeline. Then we need the 3-level basis instead of a 2-level basis, and this is actually why I prefer to use the n-level basis instead of the spin basis. If I just want to add another level, I just make a 3 out of a 2, and it's done basically. Then we also need to define again the transition operator for this. The Hamiltonian and the jumps, what I wrote there is just this simple example. So we just get the decay rate of the level 3, which is, well, which I told you should just choose 1, and the radio oscillations on this level 3 is just basically 10. Is just basically 10 times gamma. The Hamiltonian is then written like this. I think most of you may know this. Jump is just basically the transition operator from 3 to 1, which brings the atom down from level 3 to level 1 to the ground state, and the rate of this decay is just gamma 3. I defined here a population function, which gives you the population of the state. Yeah, I just like this. So if I put here 1, then it's this population of state 1. If I put 2, then population of state 2. And then I defined a list of times and different initial states. And this, okay, I just comment this one just to show you the physics, what's happening. If you start in the ground state, you should obtain sorry, I think I did not know, but I did not execute everything. So now, good. Yeah, so you should not detect any photons at all. This means state. No, wait, I'm in the. Sorry, if I'm in the ground state, you should detect photons, and this means you get a lot of quantum jumps here. If you start in the state 2, you should observe no photons at all. This means state 2 is always populated, state 3 and state 1 is never populated because we chose that state 2 should not decay. And then now the interesting case, or the most interesting case, if you start in a superposition, it really depends what kind of trajectory you have, because basically you just start in a superposition of state 1 and 2, and the atom itself decided where it goes. So it's increasing, so the probability is increasing that it is in state 2 when you don't obtain a photon or don't obtain a quantum jump. But suddenly, in this trajectory here, it decides that it will be in the ground state, which you see with this quantum jump of the orange trajectory. And if you choose another trajectory, you see that the atom basically decides that it is in the excited state, and what it does is, whenever you don't observe a photon or don't observe a quantum jump, the probability is just always increasing, and on some point it's almost 100% that you can be sure that it is in the excited state. And with this, I just leave you this one here open that you can copy.
Okay. So concludes first day of our hands-on with QuantumOptics.jl. I'm very happy seeing how many of you participated so intensely and how many questions we had. I'm really sorry for everybody who problems installing packages or getting something not to run as expected. In principle, Julia tries to work on almost any sensible platform, but apparently we've seen some issues, and I'll try to hopefully come up with some answers for you guys by tomorrow. And something that Cristoph already indicated, so of course we have some solutions for you. And again, I would like to flash the URL, because you will not find it by Googling or anything, so this is just a private site for this summer school. Please remember this. If you want, take a picture, qojulia.org, you find it, and then the name of the summer school. And we will put the solution sheets of the things we did today, so basically the notebooks we gave you, but with our, or rather Christoph's solutions filled out on this website by later this evening or maybe tonight. So you can even check it before you go to bed if you want to. And we'll certainly continue with this website tomorrow with the exercises that we already announced, namely the dissipative readout of a semiconductor quantum or semiconductor qubit, and you guys implementing the Møllmer-Sørensen or the cross-resonance gate. And with this, again, thank you for contributing, thank you for working with us, and now enjoy the panel discussion and the coffee break. Thank you.
Okay, I guess we can start and we can proceed to the second part on the tutorial hands-on session with QuantumOptics.jl.
Well, thank you so much. Again, as we had yesterday, I will well, start this with a brief introduction, recap, and then I will hand over to Cristoph for the actual coding. So what are we going to do today? A quick recap of yesterday. Yesterday we learned about how the entire framework was conceived and who is part of the framework and why we did this. Then we had the guided example of the single qubit, which as far as I saw, all of you managed to implement. Then we had the little exercise of the ion chain readout. And this basically almost perfectly in time concluded our hands-on session from yesterday. And today we're going to continue in the same spirit. Cristoph will show you a guided example in the beginning, this time a dispersive readout of a superconducting qubit. And we'll also again have some little tasks for you to fill in the notebooks, and I'll show you where to get the exercise and guided example notebooks again for today. And lastly, we'll really have a hands-on exercise session where we've prepared two interesting systems, basically C0 gates. Once in the Møllmer-Sørensen gate, where you implement this for ion chains, and once as a cross-resonance gate, where you implement this for superconducting qubits. But of course, as we learned yesterday, as long as you know your system, which means you know your Hilbert space, your Hamiltonian, your parameters, and probably also some decoherence or dissipative processes, so your jump operators and your rates, you can implement anything. And we really encourage you, if you have some particular system in mind that pertains to your own research, and you want to try this while being guided or while being able to ask for help in the exercise session, please also do so. So if you have a particular system that you would like to realize, you don't have to do the Møllmer-Sørensen or the cross-resonance. These are just offers from our side if there is nothing that you have in mind or would like to do pertaining to your own research. Okay, yesterday I promised to those of you having trouble that I will look for a solution, and I kind of found a solution, but in the end it's unfortunately still disappointing. So there is this service called CoCalc where you can use basically their computational power in the cloud, and you can do everything in the web browser. And if you go to this website, cocalc.com/features/Julia, you can find this service. You can anonymously execute notebooks there and also call up a terminal session. But unfortunately, they do not allow to add packages, which is kind of cumbersome and turns the entire exercise for us at least a bit senseless. But you could download the zip package from GitHub, upload it there, and then sort of locally on the cloud server execute it. And if you want to do this, instead of maybe just looking on the screen of your neighbor where the system is running locally, please just approach me and I will sort of show you how to do this. Or you can also sign up for a paid account and then you can add packages, but I doubt that anybody would want to do that, at least for the exercise today. So again, cocalc.com/features/Julia. This is our workaround for those of you who were not able to get a system set up locally. Okay, again, the exercises, please go to this webpage, qjulia.org/QCHS, where we again put up the exercises. Today we're going to be on the right-hand side here, so we have the guided example of the dispersive readout, and then we have our two examples or exercises that we provide to you. Again, you can also do your own systems if you want, and these are the notebooks that we have up here. And I don't know how many of you checked yesterday, but as far as we understood, there was a lot of demand for seeing the solutions quite directly after our session yesterday. So we also put up the solutions already yesterday at, I believe, 6:30 or so. So when you went out after the panel discussion, they were already there. And if somebody checked before going to bed, as I suggested, you will have surely noticed that the solutions are there. And if you haven't, you can download them today. And also today, after the session, we will put down the solution, at least for the guided exercise number 3, and for the other exercises, we then have some announcements, as Ivan mentioned in the morning. There is also the possibility to get some ECTS credits by submitting some notebooks, but we're going to tell you about this afterwards. And again, let me reiterate from yesterday, the most important resource that you have when you deal with QuantumOptics.jl is the website, qjulia.org, and you go there, and again, on the top right-hand side, you have the documentation. And in the documentation, you do not only find everything explained, also with a physical background and numerical computational backgrounds. So all the algorithms and all the ideas, the individual approaches are explained there. But, and Cristoph will show this in a second now, the documentation is also very, very rich in terms of examples. So if you're looking for some physical systems, we have many, many examples. Of course, most of them are close to what we do in quantum optics, but we also have some quantum information like entanglement or entropy, or those kinds of things, examples in there. And of course, maybe if you guys want, and you will submit a notebook and it's written on the sort of explanatory level of those examples, we're also very happy to put that up in our documentation, and of course also credit you with your name and contact information. And with this, I'm going to hand it over to Cristoph for the scrolling through of the documentation, showing the examples, and also a quick recap from yesterday.
Okay. Good. Okay. So as I discussed with Ivan, if you want to get the credit points for some example you write, then it should basically be something maybe on your own research or something like this. I don't know, some systems which is not covered now in this session here. And to get you an idea how it looks like, for example here, the cavity cooling of a 2-level atom with a small theoretical description, how it's implemented with an Hamiltonian and with the Liouvillean, and also here semi-classical equations. And then you basically put the code and explain a little bit what's inside the code. And if you do this properly, then I'm pretty sure you just get the 2 ECTS points promised by Ivan. Okay, and also there are a lot of examples, and if you get stuck by just reading the documentation how to implement something, then just scroll through the examples, think about which system is similar to yours, and you will find some solution, hopefully. Good. Okay, but before we go to the programming now, I just want to mention one other package we have. This is the QuantumOptics.jl. So the idea of this package is completely different to the quantum optics, because in the quantum optics you always do this matrix multiplication. And the quantum cumulants is a package which derives analytically equations for you in the mean field approximation, but not only just the mean field approximation in first order, that you, just not the first order, but you can also do higher orders. And the syntax is basically the same as in quantum optics, and I show you just an example to get you an idea. You have these Hilbert spaces. The difference is you need to define Q numbers, which are then basically symbolic expressions, then C numbers, which are basically just parameters, symbolic parameters. And with this, you can also implement the Hamiltonian jump operators similar to quantum optics. And then you can just define a list of operators where you want the mean field equations from. And then quantum cumulants derives them automatically for you by applying just the commutation relations of, for example, the bosonic operators or the relations between transition operators. And as you could see here, just the explanation, for example, to close the set of equation here in second order, so what I chose here is the second order cumulant expansion, you would also need the equations, for example, for A here, for the expectation value of A, just to get a closed set of equations. And this is also automatically implemented in quantum cumulant. You just need to complete your system, and then you get a closed set of equations. And this can then be historically, just similar to quantum optics. But it's a completely different approach. It's basically a mean field approach without matrices and stuff like this. And we also have a paper on this published this year, which has a detailed description how the principle of it works. And yeah, it's worth a check, I would say. Good. Okay, I don't need this. Okay, just to recap what we did yesterday, was everybody fine with the ion chain readout example? Do you have still some questions? Did something not really work for you, or should I just basically go on with the next example? Because so maybe I just mentioned briefly what we did. As always, we just need to load the packages, in our case quantum optics and Pyplot. Then we need to define the basis of our system. We need to define our operators, what we have, then the numeric parameters. We just need to get them from the system itself, or from the physical system, and then we just need to create the Hamiltonian and the jump operators, or the list of jump operators, and the according rates of our system. And usually we are interested in expectation values, and we just calculate them for whatever operator we want to have. And in the end, we just do a time evolution of the system, in this case with the Monte Carlo wave function, but it's quite easy also to use a mass equation by just replacing Monte Carlo wave function by mass, or to use the Schrödinger equation, which doesn't need then jump operators, but it's in principle the same. So yeah, that's basically what we did here for this ion chain readout example. Okay, good. So I hope this was basically clear for most of you. And then just switch to the guided example of today, which is the dispersive readout of a superconducting qubit. So Laurin will briefly explain what it's about. We already heard of it today in the morning, but we just want to mention it briefly what it's about.
That's fine. I guess I will leave the explaining to you.
Okay.
But I need to mention this email address before we move on. So as Cristoph said, as I said, and as Ivan said, so you should know by now, there is the possibility to get the 2 ECTS credits, and I promise I will not say ECTS anymore in this session. If you make a notebook as an exercise and you want to get the credits for it, please do so, and then send the IPyNB file to this address: quantum computing, hard and software, QCHS @qojulia.org. And Cristoph will get it, I will get it, and Ivan will get it, and you will get the credits that you can then use for your studies. And yeah, as mentioned also just 10 minutes ago, if you really want to put in the effort and make a very, very nice notebook that we could also use for our documentation, you're more than welcome and invited to do so, and we will certainly also mention you and link to you and give credit to you. And in that regard, if you have a GitHub account and you didn't do so yet, we would really appreciate it if you could start the QuantumOptics.jl repository, so that it gets even more exposure and it's highlighted at some point. Also.
And also the quantum cumulants.
And also the quantum cumulants, yeah. And I mean, we have other packages, so check out the add-on section and maybe star all the repositories from the QCHS group that you find. That would be really, really awesome. Thank you so much. Okay, now back to physics.
You have to change. Okay, so what you see here is the driven system, or the readout of a superconducting qubit, and what it's basically about is it's just a cavity surrounding the qubit. And the cavity is driven by some laser, it's not laser, but a micro frequency radiation. And what the physics behind it is that you, depending if you are in the ground state or in the excited state, you get different signals of the transmitted light. And what we will do is we will choose the frequency just no, sorry, such that it just centered at the peak of the blue, what is it, the Lorentzian, I think, of the blue Lorentzian. What we saw in the lecture is that the frequency was centered in the middle, which allows you to distinguish between ground state and the excited state by the phase of the outcoming light. If you choose it by the center of the blue line, then you will detect photons if you are in the ground state. No, sorry, you will detect photons if you are in the excited state, and you will not detect photons if you are in the ground state. And that's as yesterday, we just need the transition operator, which is acting obviously just on the qubit, because the transition operator is not defined on the other Hilbert space or on the full Hilbert space. But this would just give you the transition operator just on the qubit, and our Hilbert space is not just the qubit, but it's the full Hilbert space, including also the cavity. This means we need to extend our Hilbert space, our operator to the full Hilbert space, but this is basically trivially acting on the Hilbert space of the cavity. Therefore, we need just to extend it with the unitary matrix on the Hilbert space of the cavity. So we just need to include this with a tensor product. Is this roughly? Did you get this somehow? So, because this is really important. The operators need always to act on the full Hilbert space. It's not possible to just define the operator on one subsystem. It always needs to be on the full Hilbert space. Okay, but the basis on this is now the basis of the cavity, and this is now the right way to define it. But we also need now the operators for the cavity, and they are basically just acting trivially on the qubit, quantum bit, okay. And the A, I call A the destroy operator. Destroy. Yeah. So this is basically the destroy operator on the cavity. So I guess you know about this somehow. Okay, here you see what it looks like. Now I also want to define the A dagger, which is basically just the dagger of A. Okay. So with this, we basically define all the operators we need to set up the Hamiltonian and the jumps for our system. And now I will just copy the next few lines, because they are basically just the numerical parameters of the system. Yeah? You mean this one? Ah, yeah, that's true. Let's see. I just executed it. I think it's depending if it's a... Actually, I don't know, because the A operator is it off diagonal? I don't know really. So when it shows like this or this, it's depending what the shape is, yeah? Yeah, it's depending on the shape of the operator, if it's showing it like this or this. Okay, good. Anyway, so we just implemented all the operators we need to describe our system. Here I just copied the real parameters of our system, and they are just from the paper here. I can just show it to you. So this is this cavity quantum electrodynamics for superconducting electrical circuits, and obviously Andreas Wallraff is one of the authors, which was actually, from my perspective, really nice to read, because they just do cavity QED stuff, and I'm not so familiar with the superconducting stuff, so that was really nice. Good. So now we have defined also our numerical parameters, and now your task is to set up this Hamiltonian of the system, and also the jump operators and the rates connected to it. And the jump operators in our system are the decay of the atom and the decay of the cavity. Yeah, I leave you alone with this for a few minutes. With your variables, what we also need to do is to implement the decay of the qubit and also the decay of the cavity. If you don't include the decay of the qubit, it doesn't matter that much, but you need the decay of the cavity, because otherwise the photons would grow to infinity, and then they would hit the threshold of our cut of 20 photons, something like this, and then some unphysical will happen. But you could check it out if you don't include this decay. But to include more decay channels, you just need to put them in the list with a comma, and this sigma 1, 2 here is just describing the decay of the atom, and the A is just describing the decay of a photon from the cavity. And the rates are just gamma and kappa. So the next thing to do is to define the initial state. And the initial state is just given by an n-level state of the qubit. So it's living on the qubit Hilbert space, and we want, for example, to have it in the second state, so in the excited state. But that's not the full system. We need to include the Hilbert space of the photons also, and we want to start in an empty cavity because we want to get photons inside and just start with an empty cavity. Yeah. And the state of photons can either be a Fock state, it can be a coherent state. All of these different states are implemented in quantum optics. To get a Fock state, you just type Fock state, obviously. And to get a coherent state, you just type coherent state. And you just need to look at the argument, what it means. Yeah, this one lives on the Hilbert space of the cavity, and I just want to have 0 photons inside the cavity. If I want to have exactly 1 photon inside the cavity, then I just type a. But I will start with 0 photons. Okay, and then I just copy the time list. This doesn't matter what it actually is. So I just want the list of time steps I want to calculate. Did I execute this? No, I need to execute. Yeah, so we have the initial state and we have time list. And now your task is to calculate the time evolution of it and also get the expectation value of the photons inside the cavity, which are just given by the expression A dag A. So I leave you another 1 or 2 minutes for this. I think you did this already in the previous examples. Do this, so I will just show you what you need to do and maybe explain also a little bit physics. Good. We calculate the time evolution, and I started here in the excited state, which from the parameters we chose should not, so we should basically not obtain any photons inside the cavity. Why is it taking so long now? Anyway, we should not obtain any photons inside the cavity, but what we see in a second is at the beginning we don't have photons, or more or less don't have photons inside the cavity, but since we still have the decay of the atoms, or of the atom, it will decay from the excited state to the ground state, and in the end the atom will be in the ground state, and then we get again photons. So if I switch just off the decay of the atom, we would just expect that the photon number is almost not growing. And this is what we see. So it's growing because when you drive the cavity, you will also put the atoms a little bit up and down. But you see that we just have 0.2 photons compared to 3 photons what we had before. And if we start just in the ground state, we should immediately get photons, if I put it correctly. If we just start in the ground state, we should immediately get photons, and this is what we see. It grows up to 4 photons. Yeah, just immediately, more or less. Good. That's basically it of this dispersive readout simulation without caring about the other operators, and just give the embed function the full Hilbert space, or the full basis, and tell it on which basis the destroy operator should act on. So therefore you don't need to write this O times 1, O times 1, O times 1, which can be really annoying for bigger systems. And then the other thing are these dynamic time evolutions. And this is basically what you want, because usually you just don't have a drive, which is a step function. You have a Gaussian or something like this, or some curve driving field on the cavity. And this can be implemented by, for example, time evolution dot master underscore dynamic, or Schrödinger underscore dynamic. So this is just what I want to show you with this example. And yeah, basically we have the same Hilbert space as before, and I just copy it because actually I would not need it. Good. But now we need to define the sigma operator. So, okay, we don't need to define it because actually we did it before, but I just want to show you how to define the sigma operator with this embed function. So we have the embed. The first argument of the embed function is the full Hilbert space, so the full basis. The second argument is on which basis of the full basis the operator should act on, and actually this could be also a list. In our case, it's just on the first basis, so because it's acting on the qubit, and then we just write here transition as before, and this should be then again the BQB IJ as before. Okay, did you roughly get what this is doing? So it's just making life easier if you deal with a lot of Hilbert spaces, let's say. Okay, and then your task is basically, again, use this embed function to define A and A dagger, and then also include a Hamiltonian, which is time depending. I would like you to use such a function, because then we can directly use it for the first. No, it's not so important. Anyway, yeah, just define the time-dependent Hamiltonian then, which depends on some time-depending driving field. Sorry. Okay, and I just leave you for 5 minutes for this, and then it's not fully done, but yeah. I think most of you did this already, so I will just show you how I did it. How did I do it? Where is it? Okay, we need to define the A operator also, or need, but we define the A operator with the embed function. Again, living on the full Hilbert space, it's the second basis we need from the full basis, because the BC is on the second basis, and then we just need this Troy operator on the cavity. Good. And to get the A dagger operator, I will just do it dagger of it. Sorry, this will not work now. And now we should just implement this time-dependent drive, which is basically given by this eta times exponential function of minus brackets t times kappa over 3, and then still minus 3. So this is just arbitrary what I do actually. So it's not some real physical system. It's just something I wanted to do, wanted to choose. Okay, and then we also need to square this. And actually, I'm just copying now the Hamiltonian from my solution because I'm tired. But the point is that this Hamiltonian is just time depending. So we made it time depending function, and we included this time depending function for the drive. Okay, and now here we just plot how the time depending drive looks. So this is just this ether of t, just given by this Gaussian here. And what else should we do? Yeah, the next thing we need to do is to solve this dynamic time evolution. And to do this, the dynamic time evolution solver needs to get a function which is depending, first of all, on the time itself, and the second argument needs to be the state of the system. And actually, this state is then always the updated state in the time step. And what it needs to return is basically the Hamiltonian, depending, in our case, on t, the jump operators, the daggers of the jump operators. I think, yeah, no, we cannot leave this out. The daggers of the jump operators, but we need to put a dot here that all jump operators are daggered on their own. And then we also have the rates. And that's basically the function we need to describe our dynamic time evolution. And we still need to get the initial state, which I have where here. This is the initial state, and in the end we just need to calculate then the time evolution of the system, which is given by the function time evolution dot master underscore dynamic, and its arguments are the t list, the psi 0, and this function what we defined above. Good. And then we just can calculate the dynamics as I did here. Or maybe I should make a semicolon here. Okay, and I got an error now. Okay? Okay, I just look at my solution. I don't know what the typo is here, but we need to close at 1/2 sharp, so I will not look for the error now. But in principle, everything should work, and in the solution you get anyway, everything is working. Good. This time-dependent function, within this function, you could calculate whatever you want. So you can update your state in every time step, which you need basically if you want to simulate some BEC stuff or something like this, which is always depending on the state itself. What is a good recommendation for this time-depending function, or these time-depending master equations or Schrödinger equations or whatever, is don't do too much calculations inside this function, because in every time step, you will need to do this calculation. So if you can do calculations outside, so for example, matrix multiplication, if you need to get the photon number with A dagger A, just define the operator A dagger times A outside, and then put it inside this function, or if you want to have the expectation value, just define this A dagger A outside, because in every time step, it would need to calculate this operator product, which takes a lot of time then, because you usually have a few thousand time steps. Okay, so but that's basically it. What you get is this photon number, which is a little bit different from the drive when you just have these rectangular functions, but this is always because you also just have these Gaussian time-dependent drive. Okay, but unfortunately, I think we don't really have time now for the real hands-on session, so maybe I just explain you quickly how you could do it, and you can do it on your own, and if you want, you can always come to me, and if you have problems, just tell me, and I can try to help you so until Friday. If you still want to do it, you will anyway get the solutions, but you still can ask me. The first example is this Melmoth-Sørensen gate, and if you were able to do all the other things before, you will probably quite easily can implement this, because you just need to define this Hamiltonian. I wrote here this sum over the two qubits, but you don't need to define this as a sum. You can just put every term on your own if you don't know how to use the sum, but this is also just an easy function in Julia which can be implemented, or which can be used immediately. There's one important hint which you will figure out if you want to try to implement this guy here. This is the exponential function of I times, I just put it away. Yeah, it's basically the exponential function of an operator. And the problem with this is that the operator is a sparse matrix. And this exponential function doesn't like sparse matrix. If it's a dense matrix, everything is working. And if you would just try it, then you would get an error message. And in this error message, it's recommended just to transform it to a dense matrix, and then everything is fine again. But yeah, that's also part of the game, that you need to read error message and adapt your code accordingly. Good. Yeah, that's basically the Möllmer-Sørensen gate. I think you would manage to do this. And in the end, if you just calculate everything correctly, you get these three curves here, which basically are the same as these curves here in the original paper of Möllmer and Sørensen. Good. Okay. And the last, also the other exercise would be the cross-resonance gate. It's basically also just implementing this Hamiltonian. Here we just want to use not just a single qubit, but we really want to use this anharmonic oscillator as the qubit. And what we do is, if we just have a qubit, then you can also use this harmonic oscillator or this anharmonic oscillator and truncate it just with one excitation. So the cutoff is then 1. But if you want to include more excitations, you can just do this by increasing the cutoff. And I recommend it here to use 2, just that you see that the other state, so the state 2 is not really populated. And this is what you see then if you calculate it. Yeah. No, here. The population of the state 2 is basically below, yeah, 100% or something like this. Should I try to explain some physics about this, or? Yes. Okay, good. Should I try to explain some physics on the Möllmer-Sørensen also? Good. Then let's try. For the Möllmer-Sørensen, the point is, so it's a 2-qubit gate which is implemented in an ion chain quantum computer, and there the information is transformed from one qubit to the other qubit via the collective motion of the ions. And what you basically do is you shine on these 2 qubits. Is it correct? 2 different. So you shine on one qubit a laser and on the other qubit a laser, but these lasers are detuned. But the detuning in the end is such that you just reach the excited state.
And again, judging from all the questions and all the one-to-one or one-to-two conversations I've now had, thank you so much for participating. I hope it was fun for you, at least. For me it was fun, and for Cristoph and Julian, it was really nice interacting with you, and we hope you kick out using QuantumOptics.jl, and maybe some of you will find it useful also for their current and or future